The process of fabric architecture. Design. Every structure goes through its own design journey, whether it starts from a simple sketch or a more detailed architectural outline scheme. All structures require extensive design detailing to turn them into a final working plan. Designing a tensile structure is an art as much as it is a science. Throughout the preliminary design process, decisions are made on how the canopy will be constructed to meet the aesthetic, functional and engineering requirements set out by the project team. Decisions made at this point will affect the fabrication and installation methods. Boundary detailing is an essential element, falling into three main categories: curved or scalloped edges, straight edges, and fabric edges. A curved or scalloped edge generally consists of a cable enclosed in a pocket in the edge of the fabric membrane. The cables are held and tensioned at the corners by the membrane plates. In larger canopies, webbing belts are added parallel to the pocketed edge for reinforcement, but smaller structures may need no cable at all. As an alternative, it is possible to have an external cable connected to the edge of the membrane by a series of stainless steel link plates. Fabric under tension does not naturally form a straight line, so when a straight edge is required, the membrane is manufactured with a CADA or beaded edge, formed by sealing a flexible rod in a small pocket. This can then be trapped behind an aluminium clamp plate, bolted directly onto the structural steelwork, or slid into an aluminium luff track extrusion. A fabric edge can also be curved and fixed with clamp plates or luff track. Such edges normally require flashings or cover plates to ensure the edge is waterproof. Engineering.
The function of any shelter, any structure, is to stop nature impinging on your environment. Environmental loads, wind loads, suction, pressure, snow loads, snowdrift, they attack the fabric and the fabric withstands it. However, unlike traditional construction, they deflect to a degree more than a solid house. So there is movement, and it's through the movement and the small stretching and the stressing of the fabric that the fabrics will withstand those environmental loads. They're designed to do that.
The strength of a fabric structure and its ability to resist loads comes predominantly from the tension at which the fabric is maintained at.
Because of the nature of tensile structures, they have to be heavily engineered. I can provide picturesque designs, very flowing designs, very attractive to the architect, to the client, but I also have to make it work. There's a very large load in this fabric skin that is going to be transferred somewhere, whether it's contained within the structure itself or whether it goes back to the ground, whether it goes back to the surrounding building. If we don't put enough tension in the fabric and the wind picks up, then what you can get is a massive distortion of the fabric. And by distorting the fabric, that will increase a load back into wherever it's going. But also, the wind blows over the top, the canopy will actually lift. And what will happen with a strong wind is if the fabric isn't tensioned correctly, it'll flutter. That's why there's such high loads going back to the ground level or back to the frame or back to the building.
Canopies can contain their tensile loads within their own structural framework, transferring the load into concrete foundations or ground anchors. Or they can transfer their loads onto an existing structure. However, the large lateral loads often require the structure to be reinforced. As part of the preliminary design process, a load analysis is derived from a computer-generated form-finding model. This provides the typical load size and direction. Then, incorporating a factor of safety, an engineer will determine the design of the supporting structure, the size of the foundations, the required material strength, and the necessary tension. The boundary details are then engineered to maintain the tension and accommodate the movement that may be generated at the canopy extremities. In many situations, consideration for the load that snow will impose on a structure is equally as important as considering its ability to withstand strong winds. With the added risk of snowdrifts, we have to be mindful that this can lead to water ponding. For areas where heavy snow load can be expected, structures are generally designed to have smaller spans and a greater degree of inclination to encourage the snow to slide off. When designed appropriately, fabric structures can withstand the most extreme weather conditions. Manufacture. Unlike traditional construction materials such as brick and concrete, one feature of tensile fabric structures is that it can be entirely manufactured off-site. Large clear span spaces are required for the fabrication of tensile structures, as the surface area of a single piece can reach hundreds of square meters, although we are usually limited by the weight of large membranes more than the size.
At the point of design, we go through computer modelling, analysis with form finding, patterning of the material. After patterning, the basic fabric form shape is taken to the cutter plotter, which is behind me, is cut and then welded together.
Using such a wide range of fabrics, it is necessary to adopt a variety of manufacturing methods to cut and join tensile fabrics. These range from advanced sail-making techniques to more industrial large-scale manufacturing processes. Welding works for the majority of our fabrics and is suitable for external use. Some fabrics are joined by radiofrequency welding. This consists of heating the thermoplastic element in the fabric coating using electromagnetic waves to soften them and bond the two layers together. Advanced welding technology allows us to create an even strength across the length of the weld and a bond which will withstand extremely high tensile loads. Not all fabrics can be welded easily, and some require an additional layer of bonding tape to ensure the weld can achieve the strength and stability requirements for this type of application. The seam is designed to have the same tensile strength as the fabric itself. Sewing is suitable for smaller projects, and for reinforcement patches on some larger membranes, we use industrial sewing machines and UV-stable thread to join the fabric layers to one another. For some applications and some types of fabric membrane, including silicon-coated glass cloth, welding or sewing are not an effective means of joining. Gluing using a high bond adhesive will provide a joint with adequate strength and durability. Installation.
A conventional building construction means that the builder arrives on site, builds his foundations and builds the building up. Our industry is not like that at all. We fabricate most of the components off-site. So in other words, we bring to site in kit form the building and assemble on site. The biggest advantage of that is that we are not getting in anybody's road during the construction phase, and it means our time on site is relatively short.
As the majority of manufacture occurs off-site, the installation of a tensile fabric structure is fast in comparison to other building materials. Designing and manufacturing tensile structures which are practical for erection is essential. Therefore, components, connections, tolerances, weight and sizes are all considered from the early stage.
The majority of an ALA project is actually off-site, not on-site, and as such, the design and manufacture are critical to a successful installation. On the design side, we need to consider not only the architectural requirements, but also we need to look at the installation method and consider how this is going to be achieved.
Installation of a tensile membrane requires an understanding of the material and its behavior. During the design and fabrication process, the membrane is tested and patterns adjusted to compensate for the inherent stretch in the fabric. When first delivered to the site, the membrane is smaller than required and only takes its intended size and form once tensioned into place using one of the many erection methods we can adopt. The skill and coordination of site operations are critical to the success of a project. Technical knowledge and experience of the construction and installation process often involves potentially high-risk operations with demanding access requirements or complex lifting operations.
There's two main skills that are required from site crews: is safety and also competence in the work that's being carried out. Safety is paramount. All our installers are qualified rope access technicians. They all got extensive experience in the use of mobile plant and working at height. The other requirement is that they're competent in the installation of fabric. Various different fabrics are handled in different ways. PVC, PTFE and ETFE are all handled in different ways.
Depending on the type of canopy or structure being installed, installation methods can vary. Some structures have masts which are hydraulically jacked up or extended with a telescopic section in order to tension the membrane and support the structure. Smaller structures can have corners pulled out with rigging screws, U-bolts, or by shortening the perimeter mast to tie back cables. Individual scallops can also be tensioned by shortening the edge cable where it connects to the membrane plate. A very common method is to pull panels into parallel luff tracks and tension by drawing out the corner plates that slides inside the luff track. Conclusion.
Tensile architecture has been fairly futuristic since its inception, using materials such as PTFE, which was originally engineered for NASA and the space industry. One of the great things about working in an industry like this is you can never fail to be inspired by the weird and wonderful designs and ideas that people come to you with. There's nothing we like more than a challenge to take something that looks impossible and make it possible.
Fabric is now more incorporated into architecture. We are asked to make fabric work in ever difficult circumstances. That's part of the attraction, that we have to have the ability to make sure that we do end up with a finished structure that is exactly what we hope it'll be and what the client expects. That's the job we do here, to make the dream come true.
As for the future, fabrics are changing, the methods that we install, manufacture and design are all changing. And as technology gets better, our job to a certain extent gets easier. But no doubt our clients will continue to make things more and more complicated, and we will revel in the challenge.
This presentation has covered the basics in what is, to a certain extent, a limitless and unbounded industry. The principles described apply to the majority of tensile fabric structures, but with so many possibilities, methods will differ from project to project and application to application. There is a wealth of information available to you in our technical library. We are always keen to discuss new and exciting projects, so please give us a call. Further reading on the subject of tensile architecture can also be found at www.architen.com.